Alrighty, we are going to just look a little bit at gas laws today. And y'all done a little bit of background work on them. We're gonna just kind of start at the beginning of the notes. So when we talk about the kinetic theory of gases, that goes all the way back to one of our first units. We also talked about kinetic molecular theory, where it kind of just real basically talks about all particles are always moving. Gases move more, obviously, than a solid or a liquid. They spread out more. And because of this, then there's some laws that can be applied to them because they can be more easily manipulated, like condensed or expanded than a solid or a liquid. So we'll start here in our notes, and there are 5 basic postulates of this theory. For ideal gases and real gases differ. We talk about ideal gases, they really don't exist. Most gases deviate somewhat from that. So starting off, particles in an ideal gas have no volume and are very far apart. Real gases do have a volume, which is going to be most of what we work with. Particles in an ideal gas move in a straight line. In a straight line path in random directions, and that is the same for real gases. Particles in an ideal gas collide frequently with the size of the container. In fact, that's what creates the pressure that we'll be working with, and less frequently with each other. All collisions are elastic, meaning that no energy is gained or lost as a result of a collision, and this is really pretty hard to do. So particles in a real gas do lose energy once they collide with something. Particles in an ideal gas do not attract or repel one another. There are no intermolecular attractions, which would be the attractions between particles, not the attractions within particles. Particles in real gases can have an attraction for each other, so there can be IMFs or intermolecular forces. The average kinetic energy of both ideal and real particles in a sample is proportional to the temperature. And for gas formulas, we're going to use the Kelvin temperature. And that works out good for these calculations because there's no negative numbers on the Kelvin scale. So that means as we increase the temperature, which is going to be another way that you're saying you're increasing the energy with heat, then that would increase the kinetic energy of the particles. All right, so what does all this mean? It means that ideal gases cannot form liquids and solids, but real gases can at lower temperatures. Because at lower temperatures, the particles are going to slow down. So then that gives a chance for the IMFs or intermolecular forces to increase. And if they increase enough, then it could go from a gas to a liquid. It could go through that phase change. Under conditions of a high temperature and low pressure, that's when real gases can approach or most behave like ideal gases. They also have to be nonpolar gases because they can have no attractive forces. So if they're at a high temperature and low pressure, that's allowing the particles to spread out as much as possible. And when they're able to do that, then real gas can behave a little bit more like an ideal gas. So there's 4 variables that we look at when we use to describe gases. That was on your journal for today, which is Monday, 114. Volume, pressure, temperature, and then the amount we talk about is moles, is how we deal with them. So volume is usually measured in liters. And if you remember, 1,000 milliliters is equal to 1 liter. So in other words, if I'm given something, let's say in milliliters, and I need to convert it to liters for one of my formula, then I move my decimal back 3 places, 1, 2, 3, and my numbers should become smaller. I'm sorry, this should have been 1,050 milliliters. So I wanted to convert that to liters. However many sig figs you have in your original measurement should be how many sig figs you would have when you make that conversion. Pressure can be measured in atmosphere, millimeters mercury, or kilopascal. And these are going to be those conversions, and we're going to look at them on another sheet here in a minute. So we'll see that millimeters mercury and torr are basically the same with regard to the number. So if I have 10 millimeters mercury, then I also have 10 torr. Some of the other ones are not as easy to convert. The temperature is always in Kelvin in gas laws. And once again, that's because we don't want to have a negative number. So if you have your temperature in Celsius, you simply add 273, and that's going to give you your temperature in Kelvin. Kelvin does not have a degree sign. Also, all of these different things, like these conversion factors, what we're going to look at on our formula sheet, adding 273 to it, none of those are going to affect sig figs, okay, because those are considered conversion factors. Because when we do this Celsius and add 273 to it to get to Kelvin, it's really 273 with an indefinite number of zeros. It's very exact or very significant. So that's why it does not change as far as how many sig figs that you would have. The amount, small n, is measured in moles. So if you have something in grams, you're going to have to use molar mass to convert. So our standard temperature is 0 degrees Celsius or 273 K. Write that to 0 degrees Celsius. Our standard pressure is usually considered to be 1 atmosphere, but that would be the same thing as 760 millimeters of mercury or torr, or 101.3 kilopascals. So if you say something is at STP, if a gas is at STP, that gives you information at the temperature. That means that gas will be at a temperature of 273 K, and it gives you information about pressure. That means that gas would be at 1 atmosphere. So STP stands for standard temperature, shorten that, and pressure. So that in and of itself, saying a gas is at STP gives you some information. All right, so let's look at that sheet that you picked up yesterday. Not that one. Let me get to my right subject here. All right, we will be using this reference sheet a lot. Today, we're going to go to this side, and we're really going to kind of be just using something pretty specific. So since we're going to look at pressure and temperature conversions, then we're going to be using this, and then we're also going to be using this line. This is how we would convert from Celsius to Kelvin, which is probably the most common conversion as far as temperatures. And then if we needed to convert between pressure units, we would use all of these conversion factors. So for instance, this is saying 1 atmosphere is equal to 760 millimeters of mercury. So if I needed to use that as a conversion factor, I would say 1 atmosphere over 760 millimeters of mercury. That's the same thing as saying 1. This is equal to this. The reason it's hard to see is because the numbers are different, but that's because of the units. So we're going to be using this line for our pressure conversions. All right, so let's look at a few of those. And this is what you'll have your practice on. So this little bit of notes, pressure conversions and temperature conversions are what you will see on the quiz, the open notes quiz next Tuesday, which is Tuesday the 22nd, first day of the second 6 weeks. All right, so if we're looking at these conversions, we're just setting up a quick dimensional analysis. So this is going to be our given, and that's going to determine how many sig figs. So I have 6.2 atmospheres, and I want to go to torr, so that needs to be up here, just like we did with stoichiometry. If I'm atmospheres here, I have to be atmospheres down here. So this conversion, torr and atmospheres, you would get off of that sheet we just looked at, your reference sheet. And on that it says 1 atmosphere is equal to 760 torr. My atmospheres cancel, and now I'm going to multiply across. Get my calculator out. And since there's a 1 on the bottom, I don't need to divide by anything. So 7.2 times 760. And I only want 2 sig figs. So maybe you got this in your calculator, but the correct answer would be 4,700 torr. Sorry, I tend to write a little bit big. Let's do another one here. I have 1,820 millimeters of mercury, and I want to get to atmospheres. If I'm millimeters mercury here, I have to be millimeters of mercury down here. So these conversions, I get off that line on my reference sheet, and it says that 760 millimeters of mercury is equal to 1 atmosphere. This cancels, and I'm going to do 1820 divided by 760. 3 sig figs, so my answer should have 3 sig figs, so I would get 2.39 atmospheres. All right, let's look at one more. We'll look at this one with millimeters of mercury in kilopascals. So I do the same thing, 526 millimeters of mercury, and I want to get to kilopascals. If I'm millimeters mercury here, I have to be millimeters of mercury down here. So I'm ready for my conversion. And that is there's 760 millimeters of mercury and 101.3 kilopascals. Units cancel out. I'm going to multiply across 526 times 101.3 and then divide by 760, since that's what I have on bottom. I started with 3 sig figs, so my answer should have 3 sig figs, so 70.1 kilopascals. All right, so that's your pressure conversions, and you'll have that reference sheet, so you don't even have to memorize them. On your temperature, we're going to worry about moving between Kelvin and Celsius. So if we have it in Celsius, to get to Kelvin, we need to add 273. So on this first one, I'm just going to kind of move it out here, 10.12. That's Celsius. I'm going to add 273. Remember, my rule for adding or subtracting sig figs is places behind the decimal. Even though we write 273, it's really 273 point a bunch of zeros, so it does not affect the sig figs. In other words, because this is 2 places past the decimal, I want my answer to be 2 places past the decimal when I change it. So I would end up with 283.12 K. If I already have it in Kelvin, so let's say number 1250.2 K, and I want to get it back to Celsius, I subtract 273, which is really 273 point a bunch of zeros. So in other words, because this answer, I'm sorry, because that number was 2 places past the decimal, my answer should be 2 places past the decimal. So I would take 50.2 minus 273, and I would get negative 222.8 degrees Celsius. You can have a negative number when you're talking about degrees Celsius. So that's what your practice is over that you got on making these conversions. On the day that you have a sub on Friday, you will also be doing this type of work. Don't forget, on Thursday, you have your journal test. So come in to look at my journal if you have any questions before then. And tutorial times are posted. And the quiz on Tuesday, when we come back after this weekend, will be over this little bit of notes and then these types of conversions.